Hello viewers, it is indeed a great pleasure for me to bring to you another program in the Teleschool Senior Series. The subject today is functions. As it is an important subject, we have devoted 2 programs to it, and this one is the second one. In the first program we have considered the definition of a function, the vertical line test, one-to-one function, the horizontal line test, and then continuous function and increasing function. We will revisit these topics. So, what is a function? Let's define a function. A function f from set A to set B, written as f from A to B, is a rule which associates with each element x from set A one and only one element in B. The element in set A is represented by x, and the element of set B is usually represented by fx. We will now consider some of the notations, some of the terms associated with functions. So, again, consider a function from set A to set B. fx is called the image of x. Set A is called the domain of f. Set B is called the codomain of f. And the set of images is called the range of f. So set A would be the domain, set B the codomain, fx is called the image, and the set of all images would be called the range. fx is often referred to as an independent variable and fx the dependent variable. Functions are very often associated with graphs. Let's see an example. fx equal to 2x for the domain between -2 to 3, x lying between -2 to 3. Let's draw the graph. X, fx, vertical axis. The domain is from -2 to 3. The domain is usually associated with x-axis. So the domain is from -2 to 3 on x-axis. We draw the graph for fx equal to 2x. Therefore the range would be from -4 to 6. The y coordinates, or the coordinates on the vertical axis, would give us the range. The range of f would be from -4 to 6. When a graph is drawn, we usually write it as y is equal to fx equal to 2x in this case. The domain of the function f is from -2 to 3, whereas the range is from -4 to 6. Or we write it as fx from -4 to 6, or y from -4 to 6. An important type of function is the one-to-one function, or the one-one function. Let's define a one-one function. If f is a function from set A to set B, it is said to be one-one if images of distinct points of A, that is the domain, under f are distinct points of B. So, we'll take an example. F is one function. Why? Because no two elements of the domain have the same image. F is a one function. Another important type of function is the continuous function. Let's consider continuous functions. Continuous function refers to functions which are continuous within their domain. So let's take an example. Fx equal to x squared for the domain -2 to 3 is continuous. Let's consider another example. fx, there is a jump in fx here, there is a jump, so fx will not be continuous, there is a break here, so this function fx is not continuous. Fx is 0 for all negative values of x, fx equal to 1 for all positive values of x. Because of the jump, fx is not continuous. Now we're going to consider decreasing functions. So a function would be defined as decreasing if the graph, on the graph, once the graph of the function is drawn, we see that the graph is falling. So if we define y is equal to fx to be a function in the domain from a to b, then we'll see that fx is decreasing in the function, is a decreasing function in the domain from a to b if it falls, fx falls. Now, we will define decreasing function. Let x1 and x2 be two elements of the domain such that x2 is greater than x1. Suppose that we have a function fx which is continuous within the domain D. Then fx will be said to be decreasing if fx2 is less than fx1. x2 is greater than x1, fx2 is less than fx1. Then fx is said to be decreasing function. We'll show that on the graph. Let's take two elements of the domain. x1 is one of them. The corresponding value of the function is fx1. Let's take x2 such that x2 is greater than x1. The corresponding value of the function is fx2. Note that x2 is greater than x1, but fx2 is smaller than fx1. So fx is decreasing if fx2 is less than fx1. There is a condition, the derivative condition, which can be used to verify or prove whether a function will be decreasing or not, or if it is decreasing, for which values of x in the domain it will be decreasing. So let's consider the derivative condition. If fx is continuous within the domain D and f dash x is less than 0 for all x in D, then fx is decreasing. That is, if fx is continuous in a domain D and the derivative of fx is negative for all x in that domain, then fx will be said to be decreasing in the domain D. Consider the function fx equal to x squared. Is fx a decreasing function for all x in the domain which consists of all real numbers? No, because we find that for positive values of x, fx is rising, whereas for negative values of x, fx is falling. So fx would be decreasing from the graph. It is clear that fx would be decreasing for negative values of x, but fx would be rising for positive values of x. Let's verify that by drawing the graph of the negative part and verifying whether fx2 would be less than fx1. Consider the negative part of the graph. That is the graph for the negative values of x. Consider two values of in the domain x2 and x1. Clearly x2 is greater than x1, but fx2 is less than fx1. So x2 is greater than x1, but fx2 is less than fx1. Therefore fx equal to x squared is decreasing only if x is less than 0. We will now apply the derivative condition to fx equal to x squared to prove that fx equal to x squared is indeed decreasing only if we restrict the domain to negative values of x. So fx equal to x squared, if you differentiate, you will get 2x. You will agree with me that 2x will be negative. That is, the derivative will be negative, less than 0, only if x is less than 0. So fx equal to x squared is decreasing only if we restrict the domain to negative values of x. We will now consider evaluation of a function, which is an important part of function. Now, unless stated otherwise, the domain of a function that is given by a formula will include all points where the formula makes sense. Points where the formula does not make sense will be excluded from the domain. We'll take an example. So for this function defined by x plus 1 over x minus 2, the domain consists of all real values of x except x equal to 2. The function is not defined for x equal to 2. So we'll say that the domain consists of all real numbers except x equal to 2. And in that domain, fx is continuous. During the evaluation, we will consider only values of x within that domain. That is, we will not evaluate fx when x equal to 2 because it is not defined. So let's take an example. If fx equal to 2x squared minus x minus 3, let's find the value of fx when x equal to 3 and fx minus 2. Note that in a function, x is simply a placeholder. That is, anything can be substituted in the place of x. For example, instead of writing fx equal to 2x squared minus x minus 3, the same function can be written with u, fu equal to 2u squared minus u minus 3. Or simply f of the parenthesis equal to 2 times the parenthesis to the square minus parenthesis minus 3. Anything can be replaced in this parenthesis taken from the values in the domain. So to obtain f of 3, we simply replace 3 in this parenthesis. To obtain f of x minus 2, we'll replace x minus 2 in this parenthesis, or we'll replace, instead of writing u, we're going to write x minus 2. So to evaluate a function is very simple. We just need to replace x by the value or the expression which we are using to evaluate the function. So to evaluate f of 3 when fx equal to 2x squared minus x minus 3, we are going to write the function as follows, and then replace the parenthesis by 3. So f of 3 is 2 times 3 to the square minus 3 minus 3, which is 12. F of x minus 2 would be f of x minus 2, 2 times x minus 2 to the square minus x minus 2 minus 3, which we simplify to obtain. This means that whenever you are evaluating a function, the element which is used to represent elements of the domain like x, y, u, you need simply to replace them by the value or by the expression. For example, in the example that we discussed, we have replaced x by 3 to evaluate f of 3. Or we have replaced x by x minus 2 to obtain f of x minus 2. We will now consider an important topic within function, which is the composite function. We'll show how to combine function. In fact, evaluation of function has been extended to obtain composite functions. So, to combine functions, to obtain composite function, we'll use the following notation. So we are combining the function f and g. We can write it simply as f of g or fg. It will be defined as follows. Fgx is f of g of x. We are going to read it as f of g of x. Note that we can combine two functions to obtain various composite functions. For example, if you have two functions f and g, you can combine them to obtain a composite function fg or gf or ff, ffg, ggf. You can have many combinations from two functions. But one thing that you need to note is that combination of function is not usually commutative. That is, usually fgx will not be same as gfx. Note that when evaluating fgx, the function g is used first, and then we use the function f. That is, x is used as an input to function g first to obtain the output gx, which is used, the gx is now used as an input to function f to obtain fgx. So whenever you have to find the function fgx, you've got to use the function g first with x as the input to the function to obtain the output gx, and then use the gx as an input to the function f to obtain fgx. Which means that if you want to obtain the function gfx, you would use the function f first and then the function g. That is, use x as an input to the function f to obtain the output fx. Fx is in turn used as an input to function g to obtain gfx. Composite functions may or may not exist. It is not always possible to obtain a composite function, that is, to combine two functions. Let's see the condition which allows us to combine two functions. F of g of x exists only for values of x in the domain of g, for which gx is in the domain of f. That is, if we want to combine f and g to obtain the composite function f of g of x, we must make sure that the values of gx are included in the domain of f. That is, gx is part of the domain of f. We will now consider some notation associated with composite function. As I said, if you have two functions, you can combine them in many ways. So let's consider some of the notation that we will be using. F of x can also be written as f of x or f squared x. F of x can be written as f or f cube x. Similarly, f of g of x can be written as fgx. So we can write it as f of x or f squared, or f as f cube x, ffgx as fgx. We will now take an example to show to you how to combine two functions to obtain a composite function. Let's consider the function fx. equal to x squared minus 4x for all real values of x. Gx equal to 2x minus 4 for all real values of x. We'll find fgx and gfx. To find fgx, we'll use gx as an input to the function f. So, fx. To find gfx, we'll use fx as an input to gx, and then we simplify to obtain the composite function. Note that fx is x squared minus 4x, which means we can write it as fu equal to u squared minus 4x, or simply f parenthesis minus parenthesis to the square minus 4x. And inside the parenthesis, we'll write gx. That's why f of gx would be gx, f of gx would be gx to the square minus 4 times gx, which we simplify to obtain 4x squared minus 24x plus 32. Similarly, g of fx, to evaluate g of fx, to find the function, the composite function g of fx, we'll use fx as an input to gx. Because gx is 2x minus 4, g of f of x would be 2fx minus 4. So fx is used as an input to the function g to obtain gfx. We'll take another example to illustrate to you how to combine two functions. Consider the function fx, which maps x onto x plus 3 for all values of x in the domain of the set of real numbers. A function gx equal to x squared for all x in R. Show that there is just one number x such that gfx equal to fgx. Again, to evaluate fgx, we'll use gx as an input to fx to obtain x squared plus 3. To obtain gfx, we'll use fx as an input to g to obtain gfx. And then we equate both, since we are told to equate both in the question, and we solve to find x equal to minus 1. So there is only one value of x in the domain, which will make gfx equal to fgx. So gfx is not always equal to fgx. Remember, for fgx, g is used first and then f. For gfx, f is used and then g. Now, we'll take an example, because we said that not always fx and gx can be combined to obtain fgx. We'll take an example in which such a combination will not be possible. Let's consider the function fx equal to exponential minus x, defined for the domain x greater or equal to 0, x real, and gx equal to x squared plus 2x minus 15, x greater or equal to 0, and x real. Does the composite function fgx exist? Now, recall that for fgx to exist, the range of the function g, that is the values of gx, must be included in the domain of the function f. So let's find the range of the function g. Now, since we have restricted the domain to positive values of x, the range of g would be given by gx is greater or equal to minus 15. So the range of gx for the domain x greater or equal to 0, x real, would be given by gx greater or equal to minus 15. Now, fx is equal to minus x, x greater or equal to 0. Domain of fx is x greater or equal to 0. That is, fx accepts only positive real numbers. But the range of g is gx is greater or equal to minus 15. That is, gx can be negative. But f of gx does not, fx cannot accept negative real numbers. Therefore, f of gx cannot exist if gx is negative, because fx accepts as input only positive real numbers. But from the graph we saw that g or gx can be negative as well. So f of gx does not exist in this case. We will now consider another special type of function called the inverse function. So not all functions, first of all, will have an inverse. Inverse function are important function in all spheres of mathematics. Let's consider inverse of one-to-one functions. If f is a function which maps x onto y, then f inverse, if it exists, will be a function which will map y onto x. So we'll write f is a function which maps x onto y, whereas f inverse is a function which maps y onto x. Now, the only functions which will have an inverse are those for which each output in the range come from only one input. So this is the condition for the f inverse to exist. Let's take a few examples and I will show to you how to find f inverse whenever fx is given and whenever f inverse exists. Consider the function fx, where f is equal to 2x plus 5. That is, f maps x onto 2x plus 5. F being linear, f will be 1, 1, and the range is R. Therefore, the inverse of f would exist. The first method to find f inverse will break the function as follows. So f, when x is used as an input to function f, f doubles it to obtain 2x and then adds 5 to it to obtain 2x plus 5. Therefore, in this first method, to find f inverse, we're going to go backwards. That is, first of all, we will subtract x. Instead of adding 5, we'll subtract x, and then instead of doubling x, we'll half it, so that x subtract 5, x minus 5, half it, half times x minus 5. So f inverse is half x minus 5. F inverse of x is half x minus 5 for all real x. We will now consider another method whereby we'll use the formula and inversion of the Subjacob formula. Let's consider method 2. For the same function fx equal to 2x plus 5 for x real. First thing to do is to say let y equal to 2x plus 5, so that we make x the subject of formula, and x is given by half y minus 5. So note that x was in fact f inverse y. So f inverse y is half y minus 5. Or we can write it using x. So f inverse x is half x minus 5, because these variables are in fact placeholders in function. So we could have written f inverse u equal to half u minus 5. There is an important relationship between the graphs of the function and its inverse. That is, the graph of fx and the graph of f inverse are reflections of each other in the line y is equal to x. So let's see. If f is 1, 1, the graphs of y is equal to fx and y is equal to f inverse x are reflections of each other in the line y is equal to x. Note that if you reflect y is equal to AB, if you reflect the point AB in the line y is equal to x, you will obtain the point BA. If AB is reflected in the line y is equal to x, then its image would be BA. Let's consider the following function. Y is equal to x squared minus 2x. And consider 2 points on it, 1 minus 1, and B 2, 0. Now, this is the graph of the function x squared minus 2x. If we want to draw the graph of the inverse function, we just need to reflect that graph in the line y is equal to x. So we draw line y is equal to x. Note that if you reflect the point 1 minus 1, we'll obtain the point minus 1, 1. So the image of 1 minus 1 is minus 1, 1. The image of B would be 0, 2. 2, 0 becomes 0, 2. So viewers, this brings us to the end of today's program. In this program, we have considered decreasing functions, we have considered composite function, the conditions that will allow us to combine function, to have composite function, inverse function. And as we said that not all functions will have an inverse, and that the graph of the function and its inverse are reflections of each other in the line y is equal to x. Thank you for watching us. Until next time, it's goodbye from us.